Okay. All right, so the recording is in progress. And let me introduce Professor Fisher, and then we give you the floor. Meanwhile, people can come in. So Professor Fisher is a faculty member at the physics department in University of Massachusetts, Dartmouth. He earned his undergraduate degree in physics with honors from Caltech in '94. He received his PhD in physics from University of California at Berkeley in 2002, where he received a NASA Graduate Research Fellowship. He was subsequently a postdoctoral research at Lawrence Livermore National Laboratory and a research scientist at Department of Energy, in the Department of Astronomy and Astrophysics at University of Chicago, where he was also an adjunct faculty member at the School of Arts, where he taught a popular course in introductory astronomy for undergraduate art majors. We are honored to have you, Professor Fisher. We are very happy that you could make this time. I know you are in Heidelberg at 9 p.m. giving this talk to our physics literacy for kids. And I'm so glad that a lot of kids are coming, and many of them are going to also see your talk later on. So glad you're here. Thank you so much. We are honored to have you. Please have the floor and take it away.
Well, thank you so much, Dr. Samadini. Let me get my slides up here for everybody. Here we are.
Just make sure you're muted, okay?
So today we're going to be talking about a pretty incredible topic, which is exploding stars and the fascination of exploding stars. That's something I work on and something we'll be talking about today. So what we'll have like sort of three parts to what we'll talk about. The first part is a brief history of stellar explosions. We'll learn about a really cool stellar explosion that, believe it or not, went off over 400 years ago, but we can still see the light from it today. And I'll tell you exactly what I mean by that in a few minutes. In the second talk, we'll learn how these stellar explosions can be used to map out the universe. When you measure distances, you can take out a ruler if you have something in the room, but in the universe, there are no rulers in space. So how do you measure distances in space? Alec, do you have a question?
So if you can still see the light of it today, that would mean that it's more than 400 light years away, right?
Yes, exactly, Alex. So when you see a light from a star, they are so far away, like you're saying, even the nearest star is, we say, 4 light years away. A light year is not sounds like a time, but what it is the distance that light travels in 1 year. So the nearest star, like Alpha Centauri, is 4 light years away, meaning it takes light that long to get to us. 4 years. That's the nearest star. Do you know how big the galaxy is? Sorry, Rex?
I just said go supernovae.
Yeah, exactly. So these supernovae we're going to be talking about are way, 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 way more distant than that. They're hugely distant. They're not even in our galaxy. They're in other galaxies for the most part. But the first one we will be talking about will have been one that went off in our galaxy. And then the last part, I'll tell you a little bit about like how these stellar explosions actually happen. We're going to, like I say here, we're going to kind of jump into the cauldron and see things as they were as they exploded. Okay, so to begin with, we're going to talk about a brief history of stellar explosions. And we're going to start with an explosion that went off a long time ago. So there was a Danish astronomer, this fellow named Tycho Brahe, and he went out on the night, November 11, 1572. We know the exact night he went out. And this fellow, Tycho Brahe, he was, even at this point, even though he's a pretty young person, he knew the location of every star that you could have on the night sky by memory, just by the eye. Do you know why he only used his eyes? Can you guess in 1572? Why he didn't use a telescope? Yes, Rex?
I think there's so much delay that when I lower my that when I like when I do things like there's like a lot of delay, like a couple second delay because of our position. So I
That's
lowered
okay.
my hand because then I thought it wasn't. I didn't know actually, but delay made it so I was still raising my hand.
Uh,
I think Akshay wants to say something, and then Alec, maybe. Akshay, go ahead.
So is it because they might not have had telescopes?
Exactly. Galileo invented the telescope in 1609, right? Or around 16 something, right? This is about 3 decades after this. So we're talking about a time before telescopes. Everything had to be done with just your eyes, right? So Tycho looked at the night sky and he saw something that totally blew his mind. He saw a star on the night sky that wasn't there the night before. Why? Well, he knew every single star on the sky by memory. So why would that be so shocking? Why would it be so shocking to see a star that you had never seen before? Can you guess? What would be so shocking about seeing a new star?
Yeah, Sirish, go ahead.
At the time, I'm pretty sure there wasn't much of a knowledge about how new stars are created and basically the life of a star, how it can go out and be created.
Yeah, exactly. Like you were saying, Suresh. In fact, there was so little knowledge. You know what people actually thought about stars? They thought that all stars basically lived forever. They were eternal. They didn't have a birth. They didn't have a death. They just stayed there forever. So when you saw a star for the first time, that meant that that was something that was completely unexpected. It just did not fit into anything that anyone ever expected. Now, when people thought about that and when it's recorded, people often talk about Tycho. If you look at this, almost everything is about Tycho. But what we also know today is that Tycho collaborated with Sophie, who was his sister. Sophie Brahe was her maiden name. And today in science, a lot of publications, when people write a paper, when they discover something, everybody's name is put on the paper. There's the students who work on this, there's the professors, everybody's name is put on it. But back then, that wasn't really done. So Tycho's name is recorded, but really they both collaborated on this. If it was recorded today, they would both have been recorded as collaborators. So this is that publication that he wrote. It was called De Stella Nova. You can kind of guess what that means, right? Nova sounds like new, Stella sounds like star, so it means like the new star. And this shows the constellation where the explosion went off. And a constellation, think of a map, right? When you look at the map of the United States, every location is in a state, right? States divide the United States into different regions. That's what constellations basically are. You think of them as the stars that connect, that you can connect on the night sky, but really think of them more like maps, states on a map. The constellation of Cassiopeia is that region that's part of the sky that you can see. And you can see here that there's a object which is marked, which is called the Nova Stella. So he marked the location on the sky where he saw this explosion, right? So what does it look like today? This is kind of a sketch of what this would look like. This is not real. This is an artist's rendition, but there's the explosion. That's the star that went off on the night sky. And over time that faded, right? That supernova, if you were looking up with your eyes, it would have faded. But if you could see it in the night sky, in the X-rays, the same kind of part of the spectrum of light that you experience if you go into the hospital, if you have something like a broken arm and they X-ray you, right? They use a different kind of light. It's basically also light, like visible light, but it's a lot more energetic. So it penetrates right through your bones. You can see it, and that's why they use it. But you can also use it to see very, very hot gas in space. To see this, you have to go into space. You can't see the X-rays on the ground because, fortunately for us, that very high energy radiation is blocked by the atmosphere. So the only way, how do you see it? If you can't get it on the ground, what do you got to do? Can anyone guess?
You have to see it from like orbiting satellites.
Exactly. Exactly, Rex, right? That's exactly what you do. So this image was taken by an orbiting satellite called Chandra, right? It's a X-ray space telescope. It sits out in space. NASA operates it, and we can see that leftover stuff, which is called a remnant. A supernova remnant is sometimes hundreds, thousands of years old, and you can see it today using an X-ray space telescope. Pretty cool, huh? Right? So that's what it looks like in the X-rays. This other stuff or around it, those are just stars, right? But the part in the center, that's the leftover explosion.
Professor Fisher, Xavier is asking if the supernova was too far away to be seen as a star. He's kind of, yeah, he's wondering, how can you see it? Is that possible to see it as a star?
Well, that's a really, really good question. So the star that exploded, we don't know exactly what went off for a couple of reasons. One is Tycho lived a long time ago, but we think, and I'll tell you why in a little bit, we think the star that exploded here was probably a very, very small star, a very, very dim star. It's called a white dwarf. So even with modern instruments, for this kind of stellar explosion, no one has ever seen the star that has gone off. But there are other stars. A really, really famous one went off in 1987 in a small galaxy. It's kind of like people call it a cloud, but it's really like a mini galaxy close to our own galaxy. It's a dwarf galaxy is really the technical name for it. So in this large Magellanic Cloud that's near the near our galaxy, in 1987, when that supernova went off, people saw the explosion, and then they went back and they said, whoa, 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 what was that? So they went through the archives at that same location, and then they saw the star before the explosion. But that was a different kind of star. That's a kind of like a really, really massive star, much, 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 much bigger than our sun.
A
And
red
it's
dwarf.
easy to see. Sorry, what was that, Rex?
A red dwarf.
A red dwarf. A red dwarf would be a little bit like our sun, a red giant. A red giant.
That's what I
Yeah.
meant.
Yeah. And that's what everyone expected. And it turns out even more surprising because that one turned out to be a blue supergiant for reasons that no one had imagined. They thought it was going to be a red giant. It turned out to be a blue supergiant. So that brings us to this question, right? What exactly, almost the same question that you were saying, right? So what did Tycho Brahe actually witness in 1572, right? That's a really good question. And you might say, well, who knows? How will we ever know, right? Because that was hundreds of years ago. Alec?
Was it two red dwarfs colliding?
That's one possibility. To be honest, and we'll talk about that at the very end of the talk, we don't really know what the actual stars that would have exploded were. But there is something we can know from what Tycho saw. And to explain this, I'm going to talk a little bit really briefly about the life cycle of our sun, right? Our sun, does anyone know how old our sun is? It's pretty old, right? It's much older than me. It's about 4.5 billion years old. 4.5 billion, that's with 9 zeros on it, right? Years old. How we know that? And that's also interesting, right? Because, for instance, you can go to the moon, you can also on the Earth, you can dig up rocks, and you can use physics to date the rocks. The rocks have some kind of radioactive material. The radioactive material decays over time. And so you can date the rocks very, very, very accurately, even very, very old rocks. The Earth is a little harder to do this technique because stuff gets weathered, but the moon you can do this on really easily. Barjor?
Isn't that type of dating called carbon dating with carbon-14?
Yeah, that's essentially the same idea, Barter. That's really, really great, right? So carbon-14 dating is a kind of technique like that because carbon-14 is radioactive. But because have you ever heard of something called the half-life? So like something like carbon-14, it doesn't live forever. It lives for a certain amount of time. So carbon-14 is good for kind of like, I forget now, but like sort of like thousands of years, right? To get like this really, really old stuff, it's same idea, but you got to use like other kinds of elements. And really the technical term for that is isotopes, right? Like a specific kind of atom that decays. So if you use those other isotopes, you can date these really old rocks. Akeem?
What is the closest black hole?
Well, that's a really good question. The closest black hole. Well, let me say two things about black. So everyone's probably heard about black holes, right? Black holes are really cool. So one thing about black holes is that there's probably like a lot of black holes out there. And don't worry, they're not that scary. They just sit out there. They don't really do very much. But there's probably something like billions of black holes in the galaxy, just old stars that blew up, went off. And there's probably black holes practically in our own stellar neighborhood. I mean, by that I mean, like as we were saying earlier, maybe a few light years away, a few tens of light years away, something like that. But if a black hole is just sitting there by itself, like the name suggests, it's black, right? You don't see it. So the only time you really see a black hole is when it's very close to another star, and then it can also shine in, believe it or not, X-rays, like the one that we're seeing, the images that we're seeing earlier with Chandra. So I don't exactly remember the very closest one, but there is a very, very famous one at the center of our galaxy, which is really huge. And that one is around something like 20,000, 30,000 light years away. We're about that distance from the center of our galaxy. That's a really huge one. The technical name for that one, if you want to impress your friends, that's called Sagittarius. Sagittarius A is the name of that one. Okay, so our sun, right? Our sun is 4.5 billion years old, right? But it doesn't live forever. Just like when you have like your car and you want to go out and pump gas into your car, at some point in time, your car is going to run out of gas if you're running on gas. Or if it's an electric car and the battery dies, there you are, right? Your battery is out of energy. So our sun, well, it doesn't have gas. It doesn't have a battery. What does it have? What's in it? Akshay?
I think it's like nuclear fusion, like where hydrogen can fuse to become helium mainly, and then in bigger stars, helium can fuse and all that stuff.
Yeah, exactly. So our sun has the most common element in the universe, which is hydrogen. Eventually, though, that hydrogen is going to deplete, right? And this timeline shows what happens, right? As it depletes, it becomes a giant star. The giant star blows off. It's so hot, it blows off its outer atmosphere. And what's left behind is the core of that star, right? Which is a very, very weird object, right? What's left behind is the core of the star. For a star like our sun, that's about like, say, little bit more than half, what,
A neutron
0.6?
star.
Like a neutron star. Neutron stars are even weirder than this. A neutron star is even denser than this object we're talking about, like, which is a white dwarf, right? A white dwarf is like a neutron star, but a neutron star is like jammed in way, way, way more. A white dwarf is the mass of our sun, or something like that, about half the mass of our sun. Guess how big it is? If you put in the solar system, it'd be about the size of our moon, right? Or thereabouts, or maybe the size of the Earth, depending on the mass. So it's really tiny. Imagine taking the whole mass of our sun and jamming it in to the Earth. How dense do you think that is? Akshay?
I don't know if this is about a white dwarf or a neutron star, but I heard that if you take like one tablespoon of the material, it weighs like many, many tons.
Yeah, exactly, right? So sort of like the number I remember is if you scooped out a spoonful, a teaspoon is about, I'd say about like, if you're using metric units, about a centimeter cubed. It's about 1,000 tons, 1,000 metric tons, so 1,000 kilograms. Rex?
I'm going to guess how dense it would be if you packed that sun into the Earth. I think would be as dense if you packed 3.5 Mount Everests in a space the size of my laboratory.
3.5 Mount Everest. I'm gonna say it's about right. I don't really remember how massive Mount Everest is, but I think probably more or less that's about right. So you got this object. It's a white dwarf, right? But here's the thing. White dwarfs are stable, right? A white dwarf like that's left over there, it doesn't explode. It's like our sun is going to wind up. It's going to be very happy just sitting there, and it will just cool off for many billions of years. But what can happen is that white dwarf can then subsequently explode if it's in a companion with another star. So this kind of shows this sort of broad evolution. So there's two kind of broad branches, right? We talked a little about this, right? Is that you're mentioning neutron stars, right? I think Akshay or Rex was mentioning neutron stars, right? So a massive star becomes like a red supergiant, also becomes a supernova, different kind of supernova than the one we're talking about today mostly, but another kind of supernova. And it can either become a neutron star or a black hole. That's how neutron stars or black holes are formed. By the way, neutron stars are a little bit like white dwarfs, but packed in so tight. Imagine you take the mass of our sun and you pack it into, I don't know exactly how big your town is, but it's about the size of your town, 10 kilometers, right? 10 kilometers, the whole mass of our sun. Rex?
I was going to say that a neutron star is so dense that protons and electrons fuse together to make neutrons.
Exactly. That's where the name neutron comes from. It's like because you pack this in so tight, the individual constituents of atoms, like protons and electrons, which don't normally go together, you push them together and you neutronize it. You neutronize the material in there. Super weird object. But today we're talking about white dwarfs, right? So how does a white dwarf die? This is not a real image, not even a simulation, just an artist's rendition, but it shows you what can happen, right? So you take a star, a companion star, and then you pull mass from the companion star. The white dwarf pulls mass onto its surface. We say it accretes it. It eats it up, right? Accretion is the technical term. So it eats up all this mass, piles it onto the surface, builds up its mass, and can undergo an explosion. A thermonuclear explosion. It's a very, very energetic explosion. And we know this is super energetic because you can see them way outside of our galaxy, even in other galaxies. They're that powerfully bright. So that's basically the picture. Now, let's go back to Tycho. Remember I said that we know what Tycho saw? You probably said I'm crazy, right? That was 400 years ago. How do we know? Well, the answer is echoes, right? Have you ever like been in outdoors and you shouted off of a building or off of a mountain or something, and you hear the sound come back at you, right? And that's an echo, right? What's an echo? It's just the sound wave hitting something, reflecting, coming back, you hear, right? And sometimes you hear the echo because depending on the buildings or the mountains, whatever's around you, you hear the sound coming back again and again and again because it keeps on bouncing back. So this little cartoon on the right shows just like sound, light can echo in space. So light can come from a different source directly to you, just like that, or it can bounce. It can bounce. You might say, well, how does light bounce in interstellar space? Isn't interstellar space empty? How can it bounce? What's out there to make it bounce? Sirish?
There's typically some sort of a small, like, there's a lot of dust and gas and other smaller objects out there.
Yeah, exactly. Just like Suresh was saying, there's a lot of gas and dust. There's stars and stuff like that too, but when you think about it, space is super big. Even stars are not that big really in space. But gas and dust is very extended and it can cause the light to, we sometimes say scatter, right? Can kind of bounce. And so you can see it on these indirect paths, not just like days later, but years later, even in the case of the supernova we're seeing, centuries later. And here's a little animation of another light echo, not from the supernova we're talking about, but from a star. Look what's going on here. This object is called V838 Monocerotis, which means basically the unicorn, a single horn animal, right? So this is a constellation like we were talking about earlier. What's going on here? I mean, it looks like something's exploding, right? It looks like something is moving out there, like it looks like an actual explosion, but this is not an explosion. The gas and the dust is there. It's kind of just sitting there, and you're seeing the light echoing from an outburst from the central star in space, right? So you're seeing that same light echo. And you know that because you can take a spectrum of the light and you can see it's the same light just bouncing around. Okay, so that brings us back to Tycho, right? Tycho, that star that exploded, underwent light echoes. And again, this is an artist animation of what this looks like, right? So you have the original explosion, right? The original explosion went off hundreds of years ago. In fact, even earlier than that, the light on Earth was first detected 1572, right? By the way, you can see that light echo that is bouncing around. That light echo bounced around in interstellar space for hundreds of years and then finally got to the Earth in 2008, right? So astronomers saw this light echo, and there were probably light echoes, if you're wondering what, it seems kind of really lucky to see in 2000, but it's probably like a lot of light echoes out there. They just saw this one light pulse in 2008, and you can measure the light from the echo. And this is where this gets really, really kind of mind-blowing, right? Because you're looking at the light, and this shows what astronomers measure. It's kind of cool to see the actual stuff that they measure. This is called a spectrum of light, right? So same way that if you could take a prism of light, if you've ever played with a prism, you'll notice the white light comes in and the colors get split off. And you can make an instrument from that. That's called a spectrograph. And you can break the light up and measure the brightness in different wavelengths, blue, green, red, and so on, right? So that's what's shown here. We're showing on the vertical axis of this plot is the brightness. Brighter is, higher is brighter, right? And on the other side is wavelength. And you can see the bumps and the wiggles are a little bit like a fingerprint, right? When you have a fingerprint, people say that no two fingerprints are alike. Well, these spectra, or as they're called, from stars are a little bit like fingerprints. And when you see the bumps and the wiggles, each of those is a signature of an atom. The atom kind of has different electrons in it, and the electrons have very, very specific kind of little states that they live in, little levels. And when they bounce around with very specific energies. And so they leave a fingerprint. They leave a fingerprint on the spectrum. Astronomers can look at these and they can characterize what's been seen. So they can compare that spectrum to other spectra, and they know that this is a white dwarf that exploded. This is just mind-blowing, right? It's as if, Tycho, you could go back in time and hand Tycho Brahe not just a telescope, but actually modern instruments, right? Or vice versa, that whatever was seen went through a time warp and was received hundreds of years later. But it's not science fiction, it's real science, and the light echo allows you to do that. Sirish, did you have a question?
No, I just had my hand up a bit.
All right, cool.
I have a question.
Yes.
How do we know it's from the same star? Is it because of the direction that it's coming from?
Yeah, it's the same general direction. It's a really difficult measurement to make. Every time I tell even astronomers about this one, their minds are blown that you can even make this detection. So it's the same direction, and then you have to rule out whether it's pollution from another source and a number of other things. But it's very and also when people sometimes make observations of supernovae, they also have to rule out light echoes as other contaminations.
But so why did it take till 2008 for us to get this echo? Was it bouncing backwards and forwards? Do we know why did it take so long?
I think that's also a really good question. It has to do with the geometry of the echo. So you can picture a little bit like what that would look like, right? That you have to have a very, very long path to get to. And it's most likely, it probably just bounced more or less once is the most likely, but that path was very, very long. It was basically, you can think of it like a very large cloud, probably almost hundreds of light years across. And that was what allowed the geometry to be extended by hundreds of years. A couple more questions I see. Akshay?
So I have a question. So if it has to echo perfectly on the Earth, the light, is that because there's like so many rays in all directions and there's a high probability that it hits some cluster of gas and bounces back to Earth? And if so, is it also possible that if you even go a little bit farther out, some in another direction, you might see the echo a completely different time?
Yeah, exactly. I think both of the things you say are correct, right? That at first when you hear this, you might think it's just incredible luck, right? But I think there's two things to realize. One is that the original supernova was really bright, like super, super bright. Like if you kind of worked out what this would have been like if you were near it, it would just been the brightest thing ever. We'll talk about this in a little bit, but basically you can think of a supernova as much energy that comes off from the entire galaxy, this one supernova explosion. Like, so a galaxy has something like 10 billion stars in it. This one star is 10 billion times brighter than your average brightness of a star. So that's a lot of light. And so that gives you a lot of different possibilities for, just light to scatter to you. But like you're also saying, because of that kind of geometry, and it's just like a sound echo, right? You hear an echo, but if someone else is nearby you, they'll also hear that same sound echo because of the kind of geometry of the echo itself. Sirish, you also had a question?
So with these spectra, do you need to adjust for red shifts when you're looking at them?
Well, very, very good question. So for this one that is basically inside our galaxy, redshift isn't an issue. But later on, I'll be showing you some other data that come from other galaxies, and redshift is very much a part of that. And Sirish's question, we'll talk about this in a little bit, comes about when you have an expanding universe. So just the same way when you hear a train that goes by you, you hear the train and it'll go, right? that sound that is shifting, it's sending out the same sound, but you hear it shifted, is called the Doppler shift. So in a way, the light is Doppler shifted when the universe is being stretched out. We'll talk a little bit about more of that later. Okay, so next part of this is getting into the, just actually kind of what we were just talking about, which is how you can use these exploding stars to measure distances, right? You go on the highway, you see road markers, right? That's how you measure distances on the highway, right? If you want to measure distances even like in the solar system, you can come up with really clever ways. Like you can put a mirror on the moon and you can bounce a laser off the moon and measure the distance to the moon super accurately. Or use radio waves to bounce radio off of other planets in the solar system. But when we get into space between the stars, it's not so easy. It's a very, very difficult thing to measure distances. So this is a little bit like what I was talking about earlier, right? Here is one supernova that went off in a distant galaxy, right? And it's actually not that distant. It's pretty close to us. Sometimes called the Black Widow galaxy. It's kind of shaped like this kind of elongated, flattened disk. This is called a spiral galaxy, right? And the reason why it's dark like this is because of that dust. Same kind of dust that is responsible for the light echo. It's there, it blocks out light. It's not a lot of stuff, right? If you spread it out in interstellar space, but when you look at the light from distant stars, there's enough of it there that over huge distances, it can actually seem to block out, in fact, does block out a lot of light. This explosion that went off, you can see, right? Here's the whole brightness of the whole galaxy. That is one star that exploded. Look how bright this thing is, right? Look at the galaxy, look at this. You can just tell, right? It's about as bright as the whole galaxy. Oh, Alec, did you have a question?
I've always noticed that there's like a brightest spot at the center of the galaxy. What is that? Is it like just that there are more stars there?
Yeah, exactly. So there's I think I have everyone's up here. Let me just maybe there we go. I got rid of that. So here is the center spot in the galaxy, right? And this disk galaxy, the spiral galaxy, this region in the center is sometimes called the bulge, right? Because look at this, right? It's this center here is very bright, but if you look also here, this part around it is also pretty bright. So there's a lot of stars in here, like a lot of stars, way more than if you're out here. Like look at over here. I mean, of course, it's dusty, so you can't see everything, but there's way fewer stars out here. And then the other thing you'll kind of notice, if you you have to kind of take a little bit of a step back, but notice how you see a lot of brightness all the way around it, like that. So that's also part of the galaxy. There's kind of like this surrounding region that's full of little stars everywhere. That's called the halo. And this halo, we know when you look at those stars, they're really, really, really old. There's some of these stars in the halo that surround the galaxy, like our Milky Way, are almost as old as the universe itself. So that's a really good question, Alec. The central part is called the bulge. And you know what's more, if you could look at the very, very center of the center, what's down there? What would you see? Akshay or Al?
Supermassive black hole.
Yeah, it turns out almost every galaxy, like our own, has a black hole in the center of the galaxy. And you might say, well, that's kind of amazing. For many years, people have made measurements and said, it looks like a black hole. I think there's a black hole, but you might have seen like that really famous image that looks kind of like a donut, right? Of the supermassive black hole in the center of the galaxy that with the shadow that's cast by the event horizon. So we actually, for our own galaxy and for another nearby galaxy, we've actually seen it. So deep in the very core, very, very, very tiny compared to the whole galaxy, there was a supermassive black hole. So how can you actually use these exploding stars to measure distances? Okay, so imagine you had two light bulbs, right? and you didn't have any rulers, because in space there are no rulers. So imagine you had one light bulb that was right here, right? And then your friend took the other light bulb and ran away, ran far away from you. And as they moved away, what would seem to happen? That second light bulb is going to look dimmer, right? And it turns out if you go twice as far away, right, than the first light bulb, it's not twice as dim, it's 4 times as dim. And if you went 10 times as far away, right, it would be 100 times dimmer. Why that is, you have to imagine that the light that is being sent off is collected not just along your particular direction, but it's being sent off in all directions. Almost like if you can imagine all that light will hit a big, big sphere of away from the source. So that area of the sphere doesn't drop off as linear like that is with the quantity itself, but is the square. That means the thing multiplied by itself, multiplied by itself. So instead of 2, it's 2 times 2, or 10 times 10. Couple questions, I think. Alec, did you have your hand up?
If the black hole is so big and it's at the center of where all the stars are, shouldn't it be absorbing a lot of the light?
Should it be absorbing a lot of the light? So that's a really good question. So it will absorb the light through it. But the amazing thing is, like, even for a supermassive black hole, and what do we mean by that? We mean like anywhere from like millions to billions of times more massive than our sun. But here's the crazy thing. How big is that? If you had something like, I don't know, like a few million times the mass of our sun, it would still easily fit way, way down inside our solar system. So it's a teeny, teeny, tiny dot, really. So you can't really see it very easily. The science behind the measurements, that image, that kind of donut that we've seen, is just mind-blowing because it's very, 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 very small. You really don't see it very easily. So it doesn't really block out a lot of light. It does a lot of other cool stuff down there, but it doesn't block too much light. Akshay?
So, about this light dimming thing, is it because like if you're closer by, there's like a bigger part of the light that you're receiving, and if you go farther away, the slice of the sphere gets smaller, kind of?
Exactly. Yeah, that's exactly it. You can think of it like that, right? So like uh the thing you measure is not really, when you think about it, like let's say your eye, like just imagine your eye. Your eye has a little a little part of your eye measures light energy. It's received on some little piece of area, right? So that piece of area, as you move it further and further out, is a smaller and smaller fraction. What we like to, the quantity that astronomers use is something they call flux. It's a little bit technical. We don't really see just light. You see light distributed over the area. And it's essentially that, right? Is that the flux falls off as the square of the distance. This is sometimes called the inverse square law. It's this kind of cool math. If the first time you've seen it, don't worry, you'll see it many times in the future. But if you've heard this before, it can kind of make sense that this is what's going on. Jasper?
Is the supermassive black hole's gravity weaker than the smaller black hole's gravity?
That is a really, really good question, right? And the answer is a little bit surprising, I think, right? So it turns out, right, what the gravity that you feel when you're nearby an object depends both on the distance, both on the mass of the object and the distance, right? So for instance, if I'm on the surface of the Earth, right, I feel gravity, I feel weight. But if we could imagine taking the Earth and squishing it down to a smaller body, you would be heavier. You'd be a lot heavier because you'd be closer to the center. So it turns out for a supermassive black hole, even though it's bigger, right? It's more massive, I should say, right? When you do that calculation, what the weight you would feel before you fall in, it's actually lesser. So you might have, if you've ever read a little bit about black holes, you might have heard about this thing called spaghettification, which is a really cool term, right? Basically, imagine if you put some material, you try to push a star or something close to a black hole. A black hole like the mass of our sun or a little bit bigger would basically shred that black hole, the star that would come into it. It spaghettifies the material because the gravity on the surface of that small black hole is really, really intense. It's not just the mass, but the fact that it's so small. When you get out to something as large as the supermassive black hole at the center of our galaxy, you could even, make a trip. You could go to the supermassive black hole at the center of your galaxy. The spaghettification wouldn't kick in. If you've seen the movie Interstellar, you know what I'm talking about, right? Like they actually fall into a supermassive black hole at the end. Then that's possible because you don't get spaghettified, right? You don't get spaghettified before you go in. What happens after you get in is anybody's guess. And what's in the movie is probably just mostly speculation, but it's a cool movie. In case you haven't seen it, you should see it. Sirish?
So if we're going to measure distance using this, we would need to know the actual luminosity. I mean, the light, how bright both of these stars are. Could the actual spectra help us identify maybe the type of star and brightness?
Yeah. Good. Exactly, on both accounts. If you want to know the type, you use the spectra. Remember the fingerprint. Now, the actual brightness, let's talk about that, right? So this is my little universe, right? And what I'm trying to show here is the universe as it expands. We're not getting closer to the universe. The universe is as it is, it's expanding, and the galaxies are there on this kind of projected kind of like globe. We're looking at kind of like a surface inside this universe, right? What's the main thing you see? The distances change, the sizes of the galaxies stay the same. What does that mean for the distances between the galaxies? The distances between the galaxies increases. Well, why does the universe expand, right? That's pretty weird. Why is that? Why does the universe not just want to sit where it's at? Jasper, did you have your hand up?
Shape is the universe.
Shape is the universe. Yeah, the universe has a shape to it, you can say, right? And has some geometry. Akshay?
Dark energy.
Yes, yeah. So you're stealing part of my story. We'll get to that in a little bit. But the basic essence of it is something that Einstein originally he predicted. Like if you just have space and you put in the theory of relativity, it's just kind of just mind-blowing. I just have to tell you in words. If you get into physics, you can actually work this out and it's super cool. But it turns out that space doesn't just sit there. It naturally wants to either expand or contract. And that's what it's doing. It's expanding. Just like anything else in physics, it's kind of dynamical. Almost everything is dynamical. And really, it was only our kind of narrow-minded view of how space should behave that we didn't understand that until Einstein. So when people made these measurements, you have a distant galaxy. We're shown over here. This is a little bit of cartoon. And there were expectations, right? You would see the light would come to us, and it would have a certain intensity, it'd have a certain color, but the actual thing that would be seen wasn't that. It was seeming that these objects were dimmer than what they should be for a given set of galaxies, and the light would be stretched out more. And that was kind of puzzling. How could that be that things were further away than what the universe should do just with all the stuff that we know about? So that things tended to be fainter The galaxies were fainter than they actually were. And this goes into what we were just saying. There's an additional kind of energy in the universe. So there's everything that you can think of. What are some kinds of energies that you know about? There are many. Sirish?
Say gravitational, electromagnetic, and then
Wait. Let's get a few more people. Like let's think about it. So gravitational, electric, those are two. What are some others? There's like so many.
Potential, kinetic,
Yeah, potential, kinetic. Max?
stored,
Sorry, Max, say that again.
stored.
Starred? Yeah. What's another one? What happens when I rub my hands together? You feel what?
Akshay wants to say something. Akshay, go ahead.
If you rub your hands together, it's friction. Another thing is that the other two, the other main forces are like weak nuclear force and strong nuclear force.
And what about
Yeah.
energy? What type of energy is it?
Not sure.
I'll come back to you in a second. Barger?
Thermal energy.
Thermal energy, exactly. That's the kind of energy. So friction, right? Friction is the kind of force, the energy when you rub your hands together. That's thermal energy. Schwanker?
Atomic energy maybe is what the strong force and weak force would be.
Yeah. So let me touch on that, right? So I can take anything, right? This thing here, this mouse, this book, they all have energy, right? Mass, right? Mass has energy. So atomic energy, the weak particles, Z bosons, Higgs boson, the fact that anything has mass is energy. That's the brilliant insight that Einstein had. If you've ever seen that equation, people scribble it down like it's a joke, usually like in a cartoon, like E equals MC squared. That equation is saying energy equals mass. Energy equals mass times C squared, but you can think of C squared just like it's just a kind of conversion of your units. There's a way of writing that equation down that just says energy is mass. So mass is energy. Rex?
I left my hand up. I was going to say another kind of energy, but we passed that.
No. Go ahead.
Chemical.
Chemical. That's another great kind of energy. Chemical energy. So there's all these different kinds of energy, right? All the energies you can think of, right? They don't explain this set of observations. So you can put everything in a huge bucket, all these kinds of energies, all the stars, all the particles that we're talking about, the dust, the gas between the stars, and there's another kind of dark something that's out there you might have also heard of.
Dark matter.
Dark matter, yeah. So dark matter is matter. And remember, we said matter is energy. So dark matter is energy, right? But the thing about dark matter is it's matter that is different than any other kind of matter that we see because you can't see it, right? But even adding in the dark matter, still not enough because dark matter, just like when you throw a rock up, right? The rock goes up, it slows down, right? What you need here is for the universe not to slow down. If you want things to be dimmer, you need it to be speeding up. Just the opposite that you get from ordinary matter. So that's dark energy. So now I'm going to show you another actual set of data, right? It's a little bit technical, but it's really cool to take a look at, right? So what this is the actual data that was taken by the original supernova teams, right? And on the vertical axis, we're seeing the brightness of these different supernovae. Each of these points, can you see each of the points? each of those points is one measurement of one supernovae. So how high it is how bright it is. And on the other axis is that thing that we were talking about. I can't remember, was it Akshay that asked that question about redshift, right? Redshift is a measurement of distance, how far away something is. So the further the supernova is, the further its redshift is on that axis. And redshift is a measurement of how far away something is, and it's something you can measure, because just like that train example that I was giving you earlier, when you hear the train going, you can hear the sound. The sound is shifting. The light gets shifted. You can measure the shift. So you can measure the redshift. The measurement is the distance. It's a measurement of redshift, really is a better way to say it. So there's the data points. The data points are here, and then these solid lines and dashed lines that are shown here. That's what Einstein predicted. So if you really kind of look at this, okay, and so here's just what I was saying. So going up means dimmer. So these sources down here and to the right is more distant. These over here, these points are what? Are those nearby or far away? Like these guys down here, the ones over here on the lower left. What do you think? Are those nearby supernovae or distant ones?
Nearby.
Yeah, these are the nearby ones. In fact, these are all relatively nearby, but these are very, very nearby. And these are very, very carefully measured. And then there are these more distant ones. And the other thing you can see here, there's some Greek letters, but the key point here is this line over here, this solid line represents the prediction without dark energy, right? And if you look at this, you can kind of squint and say, well, all right, it kind of looks like those points, which way? Do they follow this one or do they follow these other curves? What would you say? What's the best model? Is it the one without dark energy or the one with? Rex? Or?
With.
Yeah, with. Now, I'm kind of like, for this, you can't really do what I'm saying, right? So there's a proper mathematical analysis involved statistics. But let me show you something else. By the way, this other curve is the one with 50% matter, 50% dark energy. And you can kind of tell that's a better fit. Now, what's really mind-blowing, this is the sort of the most up-to-date supernova data set, right? Same sort of plot, right? Same sort of measurements, but now look how many supernovae have been measured in the 20 years since the other one. This dashed curve is the one without dark energy. The upper one is with. And here, the data is so good, you really don't even need a fancy statistical analysis. It is so strong when you look at this. And by the way, all these little lines here, that just says that you can never make a measurement exactly, right? Every measurement has got a little bit of mistake on it, a little bit of, sometimes people say uncertainty. So those little points are not really points, but you should think of them more like a little piece of that line that is where the point is, the observation is likely to be. All those lines and the points, they all kind of nicely fit along that curve. So by now, this evidence for dark energy is super, super strong, right? That's the amazing thing about it. It's so good, you really honestly don't even need fancy statistical analysis to see the dark energy in the data. So what is our picture of the cosmos? Take everything that you know about, all the heavy elements, all the weird particles, things like neutrinos, stars, hydrogen, all that normal matter, all the stuff you're in contact with is only 5% of all of the content of the universe. 5% of the matter and energy, right? Dark matter, the other stuff they were talking about, that adds up to around 30%. Everything else is dark energy. So this is really kind of crazy when you think about it, right? Everything that you've ever really encountered, that you have ever experienced, everything you could ever really ordinarily measure, that's the normal matter. That's just 5% of everything that's out there. Rex?
Dark matter is 27% of the universe.
Good, yeah. So there's some more precise numbers on this. These are kind of, you can think of these as round numbers, right? A little bit round, but about right. Like if you rounded up 27, it would be about 30. But that's right. It's a little bit, it's depending. And there was also, remember, when you get down to it, they're a little bit uncertain, you know, so those measurements are not 100% precise either. But the amazing thing about it is simply that everything you think about, like you, the room that you're in, the air and the room that you're in, the material of the earth that we're standing on, the hydrogen that the stars are made out of, everything that you can think of, that is essentially just 5%. And this gets a little bit uncomfortable as well, because what's the dark matter? There's a lot of possibilities, but no one really knows. No one's ever measured dark matter in the laboratory, so we don't know. Dark energy is even more mysterious. So we have this picture that seems to fit the measurements, but we don't know what those constituents are. This is like a little cartoon picture that was on the cover of a science journal the year that the observations were made, and you can see Einstein looking really puzzled at these at this expanding universe that's out there. And it's partially because he himself made the original prediction for dark energy, but then he kind of threw it out at the last moment. He said this thing is just a little bit unnecessary because of the expanding universe. But it turned out, lo and behold, it actually does exist. Okay, so last part, just the last couple slides here. Let me tell you a little bit about how these stars actually explode. We talked a little bit about a historical supernovae, that was Tycho. We talked a little bit about how supernovae are used to measure distances in the cosmos, but what is actually going on? This is an explosion that went off, I guess now it's a little bit more than 10 years ago, that went off in the year 2011. By the way, all the supernovae are just characterized by letters. You know, when people have hurricanes, they just go through names in alphabetical order. Same kind of deal with supernovae. You start with the letter A, you go to B, C, D, E, and over time, there have been so many supernovae discovered per year, people had to start going to 2 letters. So they go to like A, B, A, C, A, D, and so on. So 2011 E is one of the supernovae that were discovered towards August of that year. And you can see this is a before and after image of the same galaxy, right? Here's before, there's after. Before, after. What do you notice between the two? What's the difference between before and after? Rex?
That supernova.
Yeah, where is it? It's right there. Can you see it?
Mm-hmm.
Look here and here, right? It's actually, you say it's a little bit hard to see, but if you look at it, it's pretty easy to see once you look at it, right? And again, this is a super bright object. It's almost as bright as a big chunk of the galaxy. And the amazing thing about this supernova, was the nearest supernova that had been seen for many, many years, for almost like 100 years. So it's the first nearby supernova of this type, of these exploding white dwarfs. People they looked to see the explosion. Like, remember someone asked that question early on, can you see the star that exploded? Well, here you could look. You could look in this image over here, right? You can go in and you can blow it up, just like taking like Photoshop or something, just blowing up that part of the portion of the image. There's nothing there that anyone could see. There was no star that would have exploded. So you can't really tell from the pre-explosion image, can't really tell anything else afterwards. So what is actually going on? The white dwarfs are so small, so dim, you can't see them so far away. So how does a white dwarf explode? One of the models takes 2 stars, 2 white dwarfs, they come together and they can merge over a very long time. And when they merge, again, this is an artist's rendition. It's very easy in an artist's rendition, they explode, right? They come together by, also, it turns out, by a prediction of Einstein. Einstein predicted that when you have objects that move like this, they send off a kind of wave in space and time that causes them to merge. This is an actual simulation. So now we're looking at putting the equations of physics onto a big computer and then looking at the result. And you can see these two white dwarfs coming around like this, right? And what happens, look really carefully. There's a couple things that are really interesting about this. The second white dwarf, this bigger object, right? What happens to it? The last couple orbits, Suresh, yes.
The smaller white dwarf begins to sort of absorb it.
Yeah.
Take it apart.
So here's another question, right? Look at these two white dwarfs, right? Which of the two is the more massive? Which is the heavier one? Oh, sorry, go back here. Look at them very carefully, right? They're both moving, right? They're both moving kind of around this common sort of center of mass. Think about you and your friend both on a seesaw, right? As you go back and forth, right? You're tipping back and forth on the seesaw. What's going to happen? Akshay?
Would it be the smaller one because it's the one taking in the mass?
Yeah, it's taking the mass. Also, which one moves less? Look really carefully, right? The center of mass, somewhere is where the two objects would sort of rotate around, right? I don't know if you can see my cursor, but somewhere right there, right? Which one moves less?
Should I
Suresh?
say? Or no?
Suresh?
Would be the smaller one. It's moving
Yeah.
less, it's heavier, and the center of mass would end up being closer to it.
Yeah, so exactly. Both what you said, Akshay and Suresh, is correct, right? Both because when you look at that, just like picture you and your friend, right? If you're a lot more massive than your friend, right? You're going to be moving a lot less, right? When the seesaw tips up and down. It's the same sort of idea here. Rex, did you have a question?
I was wondering why are they colored like this?
So that's a really good question. So a lot of times when we do like visualization, the colors don't really mean very much. It's usually just meant to be a way to represent the data that is actually accurate, right? Or at least that your eye can understand. Like if you could use like just like colors of green or something, that would maybe be okay, but maybe your eye doesn't really perceive that as a big range. So we like to use a range of colors, but there are many, many choices. And it's almost always like just a choice, really just that. This is a good question. So if you took a single snapshot in time and you looked at those two white dwarfs, this would be what it would look like. So there's a central one, and then there's the companion. And here you can see, remember earlier we were talking about that process of accretion. We saw an artist rendition. This is an actual simulation showing these two white dwarfs coming together. So now we're looking at another simulation. This is a simulation now of those two white dwarfs coming together and the supernova, right? So I'm going to show this a couple times. You really have to see it a couple times to sort of follow what's going on. So the mass kind of piles on from the lesser massive one onto the more massive one. Oh, and by the way, the more massive one is smaller, right? That's pretty weird, right? If you think about if you buy a loaf of bread, you buy a heavier loaf of bread, it's a bigger loaf of bread, right? With white dwarfs, it's just the opposite. A more massive white dwarf is more compact. And that's what you're seeing here. Oops, you're seeing that exactly here. So you see the white dwarf here explodes, but what happens to its partner, its companion? First star explodes. Second star, Suresh? Oh, sorry, Max.
The supernova kind of swallows the partner.
Yeah, it kind of swallows the partner. The partner, does it survive? At least as far as this simulation went?
as far as the simulation went.
Yeah, it survives. Sirish?
Sort of strips away the outer layers of the star, leaving it more down to the center.
Good. Yeah, exactly. It strips away the outer layers. So then think about that. Okay, so you're sitting there and imagine you're this second star, and one day the star that you're orbiting has a very bad day and it just blows up, right? Imagine our sun. Our sun will not do this, by the way, but imagine our sun just kind of kablowy. One day it just sent all the mass into interstellar space. What would happen to the Earth? Rex?
I was just holding my hand up like this.
Oh, no worries. Imagine I did this. Imagine I took a string and I put a ball on the string. Or actually, an even better way to do this, I do this sometimes as a demonstration. You put a donut. You can do this, but probably not inside your house, right? Take a donut, put it on a string, and put round the donut on the string, right? You take the string, you just loop it around the donut, right? Donut is soft, right? So that string is going to slip right through the donut at some point, and you're whipping it around in a circle. What happens to that donut? Alec?
Sorry. So I think like the sun will blow away the Earth's atmosphere.
Yeah, it could do that. But let's say even after that, right? After the Earth's atmosphere is blown away, what would the motion of the Earth look like? Max?
It would just be like, ooh, blown away.
Yeah, you would just Sirish?
Just keep going in a straight line from where it was rather than staying orbiting.
Yeah. You can kind of guess it's going to move somehow. And basically, Newton taught us that things will tend to go in straight lines. Like if you don't have a force, something to keep you in motion, something to push you around, basically is what a force is, you just want to move in a straight line. So what keeps the Earth in orbit is the sun. If the sun disappears, there's no more gravitational force between us, and we just move in a straight line. So this partner star, what's going to happen to it once it's we say the primary star, that central star? What happens to when it explodes? Alec? You can go ahead and unmute, Alec.
I left my hand up.
Oh, no problem. So what do you think will happen to the second star? Once the primary star is gone, there's no more gravity to keep it in orbit, so it will Shakpur?
You'll get launched.
Yeah, it's just going to go straight line, right? Straight line motion. How fast? Really fast, like really, really, really fast. Like bullet doesn't even describe it, right? Because these two stars, they're white dwarfs. They're so compact. They are basically almost touching each other. So it's way, way, way faster star in its orbit than the Earth is. The Earth orbits about 30 kilometers per second is the kind of numbers that people will use for that, right? The kind of units that people will use. These stars are going like 1,000 kilometers per second, right? So we're talking about basically hundreds of times faster than about 30 times faster than the Earth is around the sun. So these are some of the fastest stars in the galaxy, these surviving white dwarfs. And that's the last thing I want to show you here is this. There's a mission that the Europeans have launched. It's called Gaia. And you might have heard about this, but it's a really cool telescope that's in space. Here's the Earth. Can everyone see that? There's the Earth, there's the moon, there's the sun, right? So Gaia was launched from the Earth. Where? not around the Earth, not around the moon, not around the sun, but around this other kind of point sitting out here. And this point out here is just called the Lagrange point. And it's kind of like if you imagine the Earth and the sun forming a kind of system, you can kind of sit out here at this point in space almost stably. It takes a little bit of effort because you can't just sit here, but you can sort of push yourself around and stay out there. Why would they go to all that effort to put this telescope way the heck out there instead of close to the Earth? Seems like a lot of work to do something, right? It had to be a good reason. Sirish?
My guess is there's a lot of pollution, especially like pollution in radio from Earth.
Yes, radio, and if this is a telescope measuring visible light,
It's a lot of light pollution. And the sun.
light pollution. So that's exactly it. So basically, this is also like for other instruments, like if you've heard of the James Webb Space Telescope, they also don't sit in Earth orbit. They have to be they're so sensitive, they have to sit out here in one of the Lagrange points. So Gaia sits out there and it measures stars in the galaxy. It's measured, believe it or not, 1 billion stars in our galaxy. 1 billion stars, right? Their positions, where they are, but not just like when you see the night sky, you think about it, you see just a position on the night sky, you see how many coordinates. You see where it is on the night sky, but you don't really see distance, right? So you see just 2 coordinates on the night sky. Gaia measures all 3 coordinates. It can use a technique called parallax that basically, like if you shift your eye, like if you cover up one eye and then the other eye, things will seem to move around. And it uses parallax to measure distances in space, so the 2 coordinates and the distance, as well as the speed, the velocity. So it's measured 1 billion stars in our galaxy, where they are, how they're moving. 1 billion sounds like a lot, but believe it or not, that's only 1% of all the stars in the galaxy. There's about 100 billion stars in the galaxy. So this is a little bit of an animation of what those Gaia fast white dwarfs look like. There's some of the fastest stars in the galaxy. And what I'm going to show you is kind of like a time animation of what these stars would look like if you could run it forward in time. And people can do this making some mathematical models. And you see like there's some stars in Gaia that are just like, it's crazy. They're just shooting across the night sky like that. Those include some of those hypervelocity white dwarfs and those really, really fast white dwarfs. And one of them, when you trace it back in the sky, it traces back to a supernova remnant, just like Tycho, which is also kind of confirmation of that. So that's just a little flavor of what goes on inside those stars. This is really cutting edge stuff. This is like bringing you right up to date, up to what's going on in the field right now. So what will go on in the future? Well, we have a bunch of scientific instruments. There's a lot of cool stuff out there for everyone here to get involved with and to think about, and whatever kind of science you're interested in. There's a lot of big computers these days. So you can learn how to use those big computers to analyze the data, but also to make mathematical models and simulate things. And on the other side is the actual measurements that are being made. Does anyone recognize this telescope? It's one that we just mentioned. It's not Gaia, but it's another one. Max?
The James Webb.
Yeah, that's the James Webb. This one is like science fiction, honestly. I've heard this one talked about almost since I was your age, right? This one has been planned for so long. It's so crazy. And this one is making measurements of supernovae in the distant cosmos. All right, so that's it that I have. And I'm happy to hang out and take questions. We can chat and discuss other stuff or anything anyone wants to talk about. And thank you everyone for joining us.
Wow, thank you so much. This was great. Does everybody thank Professor Fisher first for coming? We know he's it's very, very late where he is. But would you have 10 minutes, like just hang around and answer questions?
However long, I'm
Awesome.
happy.
This was a very long talk. I'm sorry you're taking so much of your time, but if anybody has
No, no.
questions, please ask away. And if you want to leave, you can leave at this point. Let me see if there's any more questions here. I'll ask one question so that people don't feel shy. You distinguish between dark matter and dark energy in your pie chart, but then at the
Yeah.
same time you said they're the same. Why is that?
So yeah, so there's both dark matter and dark energy. I think it was like this one here that we had. So dark matter is, and it's a really good question, right? Because I think they sound like they're very similar. They're both dark in the sense that they're not directly measurable, at least not in a direct sense that we can put them in the laboratory and measure them. Dark matter is thought to be more or less like ordinary matter, and there's a lot of things that people suggest for these for what the dark matter actually is. Like you might have heard about
Like rocks, for instance, that we can't see, or
that was one of the early theories. People actually had like all kinds of ideas. So people thought about like things like rocks that could be in space, that could even be like another one that's even sort of like that is like black holes, because black holes are pretty dark. But so all of those kinds of material are like the normal matter. They're like you and me and everything else around us. They're made of protons and neutrons. And it turns out that if you go back to the very, very, very early universe, everything that we see, or at least the light elements that you can see, like hydrogen and like helium and some other light elements, lithium and beryllium, they were formed in the first 3 minutes of the Big Bang. And the measurements we can make of those light elements is very kind of tightly constrained with everything else. So if you try to put in like more stuff, more of this ordinary material, physicists call it baryonic, but baryonic just means like stuff like you and me, right? More of that stuff, it doesn't predict the right amounts of the light elements. So all those kinds of early ideas about things like dust and rocks and things, and even black holes, don't quite fit into the picture of dark matter. So people talk about sort of weird particles, the kinds of stuff that people discover in these laboratories like CERN, stuff that I think you'll be hearing about in this lecture series, but that haven't yet been seen. That would be actually one of the hopes of what the LHC, the Large Hadron Collider, was supposed to detect. So like ordinary matter, dark energy, though, is a little bit different, right? Because I like to use that analogy of just when you throw a rock up, the Earth pulls the rock back down. Dark matter slows down the acceleration of the universe because it has pretty much the same properties of the rest of the matter, except it's dark. Dark energy has to be fundamentally different because it has to push stuff away, and it's has that weird property. It's unlike any other kind of matter or energy that anyone has ever predicted. It's repulsive. So I know this is going to sound super weird, but if you could imagine making having a certain setup of just dark energy, you replace Earth with just a lot of dark energy, you would repulse things away from it gravitationally. You wouldn't fall in. So that's how weird dark energy is.
Mm-hmm. Thank you so much. I think Sirish has a question. Sirish, go ahead.
So when will we use standard candles for measuring distance as opposed to parallax? What are the benefits of like each one?
Good. Yeah, that's a great question. So they're both important is the short answer, right? Because you say like I didn't get into this so much, but like so you have these standard candles, like a supernovae, right? So you don't see them in our galaxy. You see them in another galaxy typically, right? So you need to know the distance to that galaxy. Well, how do you know the distance to that galaxy, right? You need another trick, right? Because you can't use the supernova. You haven't measured them yet. You haven't calibrated them. So you need something else. So people have this concept of rungs on this kind of, they call it the standard ladder, right? Supernovae are towards the top, right? But you need to get there. The bottom rung on that ladder is parallax. Parallax is a direct measurement. Remember, that's the idea. You cover your eye, you look at something, your eyes are different distances, so you see things appear to shift. Parallax, the way it's usually measured, like if you watch, if the Earth moves in its orbit, so you can use the geometry of the Earth's orbit over a long distance and the geometry of the apparent motion of the stars to measure the parallax directly. So like for a nearby star, like for instance, Alpha Centauri is 4 light years away, people will say that's about a parsec away. A parsec is 1 arc second of parallax. So that's the first rung on the ladder, right? Still not good enough because you can't measure parallax in a different galaxy. So you need another rung in between the two. And the answer there is there are other kinds of things you can use. There are kinds of very bright stars. One of them was pioneered by different astronomers called variable stars. Those variable stars are so bright, you can even see them in distant galaxies. So if you can measure the parallax in our galaxy to those stars, you can calibrate their distance, right? So you go kind of move your way up the ladder, parallax to variable stars to supernovae. It's a difficult business. People still like debate these details, but it's now gotten to a kind of precise science, where before it was sort of very, very difficult, very challenging measurements that was not often very precise.
Thank you.
Now let's
You're
see if there's any more questions. Anybody has any more questions for Dr. Fisher, Professor Fisher? Looks like not, but I have to say that you blew Quincy's mind with your, it looks like in the chat he's showing that his mind is blown with the partner star shooting across the universe with high speed. I think that's where he started putting the stuff. That was amazing. Thank you so much. This was an amazing talk. We learned so much. This was fantastic. Thank you again. Everybody thank Professor Fisher and thank you for coming. This was great.
Thank you, Professor Fisher.
Thank you. Thank you for
Thank
joining.
you.
Thank you for the great questions and enjoy your summer.
I'm going to stop recording.